Hi, good morning, everyone. It looks like we've got about 16 people in the session. That's enough for us to get going. Good morning. My name is MK. I am the Project Resource Mobilization Lead here at Known Focus, and I'm excited to welcome to the stage Michael Sarahan. Michael is a build engineer at NVIDIA, and he will be presenting on going Plaid, striving for speed of light and CI pipelines. Michael, the stage is yours.
Hi, everybody. Good morning from Austin, Texas. Thanks for coming. 16 people is quite a lot for a CI talk, so thanks for coming. What I want to talk about today is a few things. What do I mean by speed of light? And then we'll talk about how that principle applies to what we want to do with CI at NVIDIA, and also try to share some useful patterns and stuff that we've discovered along the way in trying to implement this. So what do I mean by speed of light? I don't mean kind of like the movie style warp speed. I don't mean an Iron Maiden album. This is what I meant by going plaid, which is one of my favorite good movies, Spaceballs. And CI is rarely described as ludicrous speed. But what we do mean at NVIDIA with speed of light is that rather than approaching a problem from a point of view of, hey, this is slow, how do I fix it? You should really approach problems by saying, what is the absolute fastest that this could go? And how close are we to getting there? And then, of course, how might we get closer to that? So, speed of light is not a statement of how fast you're going, it's a statement of how close you are to an ideal. And I didn't know about that principle before joining NVIDIA about a year ago, but it is definitely a very useful engineering idea. Um, what does it mean for CI? For CI, the purpose is to build stuff and to test stuff. So assuming that we have an acceptable level of building and testing, how do we minimize the time that developers are waiting for the CI to complete? This is oftentimes like uh, how long it takes for like an important thing to get merged. You want your tests to run and verify that nothing is messed up, right? You need to minimize the cost of your compute resources, which can balloon behind your back. And you certainly need to minimize the ongoing cost of the CI configuration. So this picture up in the upper right corner is, I think it's power and communication wires and all kinds of stuff in India. And this is very much what your CI configuration can look like pretty quickly if you're not careful and if you don't kind of refine it over time. It can be totally alphabet soup. Uh, I work on something called the Rapids project at NVIDIA, and it's kind of a sub organization at NVIDIA made up of a lot of stuff that was originally intended to help do data science on GPUs, to streamline data science on GPUs. So there's a lot of different tools from cuDF, which is kind of like a pandas polars interface. QML is like an interface that makes it easy to do scikit-learn type work on GPUs and so on and so forth. We have all of these different repos in one organization on the Rapids AI organization on GitHub, and we have pretty significant cloud costs on the order of tens of thousands of dollars a month. So it's just to say that effort that we spend to optimize our CI helps in a lot of different ways. It simplifies CI stuff across different projects. It reduces our spend across different projects, and it's necessary for us. This is what one example project can look like. This is cuGraph in particular. But what you see is we've got one main job, build.yaml, and that's on the cuGraph repo, and it computes a bunch of different matrices. Anytime you see something that looks like compute matrix and then the matrix, that is a shared workflow for us. And what that means is we define the workflow separately in a separate repo, and then these top level repos call into those shared workflows. So we've got a lot of jobs in the system, and they are different. They do differ in small ways. This one's pretty uniform, but there are situations where you want to compare the different steps within one build and across many builds. So how could we do that? Telemetry is kind of this idea of monitoring things remotely somehow. There's a lot of different kinds of telemetry. In particular, people talk about three pillars of observability. And these are just three different kinds of data that are a little bit different in characteristics, but they really tie together very well. So logs, for example, are a whole bunch of data points at one particular point in time. Metrics are the value of some metric in time, so CPU usage, memory usage, things like that. They're typically not things like how long a build took, or you could. it- they're not typically like aggregate statistics of a process. They're more like a instantaneous measurement at a point in time. So they're more often pull rather than push. You have some outside server like Prometheus asking your build server, "Hey, what are your stats?" And then the build server sends them over, and Prometheus records them at that point in time. Finally, you've got traces, and traces are just all about timing. Um, what they do is they as your program goes through its flow, it will send data to a server that is recording when things start, when it stops, and also what its parent span was. So this is a really cool way to get an idea of, especially for distributed tracing, where you got a lot of different services talking, you can get insight into not only how the different services are connected, but also kind of where the bottlenecks are in each different service and different things like that. So for this work, what I've been mostly focused on is tracing. And we already had Grafana dashboards for Prometheus data. So we chose Tempo as our backend server for handling the trace data. It's not the only option. There's a lot of options for actually all these different steps. And if you're interested in telemetry, I recommend kind of searching out what might work best for you. I don't mean to endorse any particular tool here over any other. We've been using OpenTelemetry, which is a pretty new idea relative to a lot of these other tools. Telemetry is just an interface layer. It does not replace Jaeger or Prometheus or Tempo or Grafana or any of these things. It does not implement storage or visualization. It's really just a connector between all of these things. So it's a standard for what the data input and output can be. It can take data from all these different services in all kinds of different formats, import it into OpenTelemetry format, output it to all kinds of different places. You can do all kinds of intermediate processing in the middle with something called the collector. Um, and so this is a really, really useful Swiss Army knife, I call it, just to be able to mangle the data in many different formats to many different formats, and it made our job a lot easier. It also has some really nice tools, APIs and SDKs for instrumenting your your binaries. And so one of the things that I played with was how to get trace data from Conda build. And Conda build is a package build tool for building Conda packages, obviously. And it has no built-in instrumentation. But with the OpenTelemetry SDKs, it was pretty easy to kind of monkey patch Conda build without ever changing the Conda build source code, without submitting any PRs to Conda build, and get out this kind of data to say how long did each step take. So that's a really, really powerful way to be able to add telemetry to your existing um, programs and documents and stuff without massive invasive code changes. We chose mostly that GitHub Actions is where most of our interesting data is because it kind of gives us the best high level idea of how our jobs are behaving. We ultimately didn't really need this level of detail on our conda build stuff, so we kind of chose to omit this and get just this higher level data of how long we were spending on initializing containers, um, how long we spend installing telemetry, instrumentation stuff, and the rest of the build process kind of gets abstracted down into just one line. But the way that we gather this GitHub Actions data, there are a couple of ways to do that. There's a couple of existing actions that can help you do that. There was some effort to add some capabilities to the OpenTelemetry collector to work with GitHub Actions webhooks. What we found to be the easiest was to just wait until the end of a GitHub job and then ask the GitHub Actions API for this run metadata. So this link leads to the particular API endpoint that you can call to get this data, and what it'll spit out is the list of your jobs and all the steps within those jobs, and these all have timing info. And so we took all this stuff and we parse it and we spit that back to Tempo as trace and span data. What this looks like in Grafana, uh, I have this represents like one top level job. So that entire big build graph that I showed earlier for cuGraph would look like this. That whole top level thing is called a trace. Each line or each trace has many spans. Each one of these spans is kind of a pretty high level span that would contain many others. And you see that each of these is expandable, except it's a screenshot, so it's not. Um, but you can drill into these in kind of arbitrary detail as long as you're willing to instrument the different parts of your step. So for us, the right way to kind of treat this is that a service name for us means the high level job name. And then you've got deeper spans below that that represent the different steps within that child job. Grafana has some pretty cool tools for aggregation of analytics. Um, these ultimately weren't fine enough granularity for us, but they are a cool tool if aggregate statistics for a given, say, tag are enough for you. We wanted to ask some finer grained questions in terms of for a particular. We wanted to highlight spans that are unusually long, and we want to figure out why they might have been unusually long. So we want to look at all the different traits of a span, such as the CPU type, the CUDA version, GPU. Why might that span have taken too long? Once you have this data, you can think about analyzing aggregate statistics as far as like what projects are using which resources. So that's like a cost analysis, and also like, is one project hogging all of the time on GPUs? Is there anything we can do to cut down that project's use of GPUs, or do we just need to increase the pool of GPUs? This question of how long is spent waiting for all the variants of the matrix to complete is the devil's in the details here. So when you talk about a job that runs for some amount of time in a graph in this matrix, um, this whole block does not actually proceed to this next step until the slowest one of these has finished. And so we want to understand what the slowest ones are and also how long that kind of synchronization barrier is adding to our build process, because that tells us, is it worth our time to try to figure out a better way? The abstraction that we have is really nice. It's really simple. Adding the matrix elements there, and moving the matrix stuff up higher in our build stack, which is what it would take to have a more kind of like coherent um, line across our entire build stack, would probably add a fair bit of complexity. So we need to understand what potential benefit there might be. And finally, watch across time. So we've got about a 2-month release cycle for Rapids. We want to understand across that release cycle, has anything changed, and do we understand why? So this is a dashboard, really early prototype dashboard I've been working on with hollow views and panel and bokeh. And what you can do in this dashboard, again, it's a screenshot, but you can click on the different attributes that you want to select the data for, and it filters the spans by those tags. And then if you have more than one kind of a filter, you start building up the different categories. So you can start to see, oh, hey, this span duration is at a really long start time. We might want to investigate that. So how does this all work? I've talked a little bit about it, but what I want to show you guys is some of the GitHub Actions tricks that we've had to do to make this all work together. The way that we share our workflows code across all of our many different project repos is that we split the workflows into two other repos, one called shared workflows and one called shared actions. And our project repos can call into the shared workflows. They can also directly call shared actions if they need to. Those are not mutually exclusive. But what it what it kind of boils down to is that shared workflows are for things that need a matrix, whereas a shared action is something that is done as a step within a job. So that's an important distinction if you're trying to think about whether to use reusable actions or reusable workflows for yourself. My personal distinction is: do you need a matrix um, in as part of your part of your work? Um, the entries of the matrix then can call different shared actions, and these kind of universally have an implicit interface that, or a convention that we do in Rapids, where they call back to the top level repo with some particular script name. And so this is how we abstract and allow the code reuse in between here, is that abstraction to say this script will always call something called, say, build CPP. And that lets this top level repo differ in its behavior while maintaining the overall shared workflow steps. I guess let me take a step back here. Are there any questions that I can answer before I move on to this other stuff? Sorry, let me switch tabs to see. Any limitations on GitHub you're running into? Recursion depth. We don't recur too much. We have certainly run into limitations that I'll talk about in just a bit with shared actions, but we don't have. We've got this pretty straightforward architecture or whatever of top level to a pretty flat list of child jobs, and the child jobs do not call into other shared workflows. So each child job is either a normal GitHub Actions job definition with steps, or it calls into a shared workflow. And then those shared workflows don't call into shared workflows. So we don't run into recursion depth, but I will definitely talk about some of the limitations we've seen with reusable actions. And I've got another question. Did you manage to reduce the time and costs of CI? I don't have any conclusive results there yet, but I will talk about um, kind of some of the decisions we've been able to make based um, on our telemetry measurements. So this this approach of kind of centralizing and sharing the code has some major advantages and some major disadvantages. Um, this is a little bit sarcastic. Weeks of coding saves hours of designing. We argue we do the opposite. We have a pretty good design that saves us weeks of coding. If we didn't have our centralized design, then we would need to um, either come up with crazy automation tools to put up PRs to tens of repos and manage the change across many repos. Um, but on the other side, and I've been acutely aware of this as I've implemented this stuff and kind of rolled it out to some of our repos. Bugs in the centralized code will affect a lot more people at once, and the CI code is not always easy to test. It's a lot of the time it's hard to test in branches. You think that you have everything done and working on a branch, and then when you move it over into deployment on your main repos, it can break in surprising ways. So it's not all sunshine and roses here. There is a cost, but we think that the benefit outweighs the cost here. Um, some of the gotchas that I mentioned with GitHub Actions, we didn't hit the recursion depth, but we certainly struggled a lot with how to um, how to reuse code in actions and how to properly factor um, bits into actions that you might want to call in other actions. Um, it's also really hard to try to come up with ways of calling script files. So like you want to run Python or something like that in a shared action. That's it's not trivial, and I'll talk about why in just a sec. The other thing is that environment variables and secrets are pretty painful when it comes to these shared workflows and shared actions. Um, environment variables are not available in child workflows. You can share secrets into child workflows, but they're not accessible in any shared actions that you call from those child workflows. So it's tricky to get the right mix of stuff. These are two ways that exist for calling shared actions. Um, you can do this what I call by version. This is the kind of the nice way because it has the branch in it and it automatically checks out the code for you. Um, but whatever this action is, it can't use relative paths to other actions. They're not cloned. This repo is not cloned when calling this action. Um, if you code those into my action with version and branch, you can do that, but you have to hard code the branch. So you can use this in my action, but you can't use a relative path within your shared actions repo, nor can you put in a variable as the branch name. So that makes it tricky to change. If you change this, then you've kind of got to change everything in that branch to match, and it's tedious and it will bite you. One other way to do this is by relative path. So you can check out your code, you can call the action by relative path, but this is kind of annoying boilerplate, and there's some really annoying stuff to do with um, default branch and stuff like that. The other thing with GitHub Actions is that if you ever do a checkout below this checkout, so this one's going to a subpath, right? If you do a checkout of the root repo, it blows away everything that's there, and so your shared actions that you think might be there will not be there anymore. So we came up with an idea over time called dispatch actions, which we think is kind of the best of both worlds. You create in your shared actions repo something called a dispatch action. That dispatch action does the job for you of checkout and then calls the implementation. And what's nice about it is that when you call it, the environment variables do get passed into the shared action. And so this is a way of kind of setting the environment variable for what repo and what ref on a shared action you want to use. And it leads to very clean calls that look a lot like just the old call by version, but have all the advantages of doing the checkout and the references. So what this lets us do is write shell scripts and files natively. We've got Python scripts, Bash scripts, whatever we want, that aren't just in plain text YAML files. We can refer to other actions and factor our code logically and reuse actions within our actions. And overall, it's a much happier place to be. So if you guys are using GitHub Actions, please definitely check this out. Reach out to me afterwards. This pattern has been a huge development for us. There's environment variable stuff that may surprise you. So say you set an environment variable. These are ways that work in ways that you might expect. And this is what I call a typical job. But when you use shared workflows, when you're calling reusable workflows, they don't work in ways that you expect. And so if you try to call that environment variable as an input parameter to one of these, you get an error message that says, hey, env is not valid here. As an aside, why use environment variables? This kind of context global state is very useful, especially with open telemetry. It affects lots of the different SDKs and binaries you might use. It's a very easy way to pass in parameters. And so how would you pass in environment variables? This is one pattern I'll mention that that you'll find if you search for this topic, how to pass environment variables from a parent workflow to a child. I call it re-export. Basically, you have to take the environment variable, make it an output of a job, put a need on that job from your other job, and then refer to that needed output. So it's really circuitous, and it's really verbose, and it's really awful. And the way that we've found that we prefer is to just write environment variables to a file and then re-export them with a more automated script to our GitHub environment. And what this looks like in our telemetry environments is that at the start of our top level workflow, we stash our environment variables, we upload it to a file, we call our child workflow. That child workflow loads that environment variable file, mainly because instrumented binaries in this child can use that stuff. Then we wait for all our matrix variants to finish. This is missing an arrow. And finally, when we get to the end, we upload that data to Tempo. But what this is also doing is putting a bunch of junk files as artifacts in your build. And so there's an implicit step here where we clean up those files that load stuff. So I'm out of time. I'd be happy to take a question. But I hope this has been useful for you to learn about some of the telemetry tools and also some of the strategies you can take with GitHub Actions to overcome its quirks. Thank you guys for listening.
Thank you so much, Michael. Thank you so much, attendees. Unfortunately, we did run out of time. However, we can keep the discussions going in the reception lounge. Feel free to open up a board so that you can continue the discussions. I know we did have one question, but I'm so sorry we do have to end this session. So thank you again, attendees. Thank you again, Michael, and enjoy the rest of the session. Bye-bye.
Thanks, everybody. Bye.